not going to talk about yet. So there are three main subatomic particles, three main ones that we talk about. Protons, neutrons, electrons. I want you to fill out what you can for that charge, or for that chart first. So on your chart, on your little note guide, fill out what you know already. What's the charge of a proton? What's its location? What's its mass? You can just fill out what you already know. If you know the charge of a proton, will you type that in, please? Oops, sorry, I have to hit start. Now you may. You know the charge of a proton. Under the at symbol. I'm going to end this one just to see what we know already. So I'm seeing a lot of positive, +1, which is exactly right. The charge of a proton is, whoa, thought I was on the right thing, 1+, or +1. Go ahead, if you know it, click in the charge of a neutron. Not everybody's in, but I'm going to end this anyways. Excellent. The majority of you came up with 0 being the charge of a neutron. That is absolutely correct. Neutron you can remember as neutral or no charge. Okay. Electron then. And bless you. Let's end this one. Haha! Negative or 1 negative. So we got a lot of the right answer there. Good job. It is -1. So those are the charges. So it kind of makes you think, why, if we have a positive charge and a negative charge right next to each other, why aren't they going towards one another? Like magnets do. If you get magnets close enough, they go towards one another. Well, that's dealing with some of the strong forces and the weak forces that are associated with some of the particle physics that we're not going to get into yet. But just think about the fact that we've got all of this positive charge and negative charge, and miraculously, it's not going in towards each other. It's amazing. If it didn't have that, we wouldn't exist. We wouldn't exist. If all of the positives went towards all of the negatives, we would not exist. We wouldn't have atoms, which wouldn't form elements, which wouldn't form us. It's amazing. Okay. The location. We've got some stuff that are in the nucleus and some that are outside of the nucleus. Go ahead, shout out if protons are in the nucleus or outside the nucleus. In the nucleus. What about the neutrons? Yeah, those two in. And electrons. Outside. And we say that those are in energy levels. In energy levels. Which sometimes we call shells. Except they're not quite as fixed as that would make it sound. It's hard to think on such a small level that these atoms are on, what type of scale we're really talking about here. So one way to think about this, if we had the nucleus being the size of a pinhead, so if you've ever done any sewing and you use those teeny tiny pins to get the two pieces of fabric together before you put them through the sewing machine, the very tip top of that head we could say is the nucleus. The average size of the atom then would be out to the final length of 20 meters. So we have this teeny tiny pinhead, and 20 meters is the size of this. And we don't have a whole lot of electrons there, which means an atom is mostly empty space. It's not like the gas laws where we had the beakers that had air in them, and that's why if you inverted it, nothing would go in because there was no place for the air to escape. The atoms don't have things in between, at least that we've found yet. They keep doing experiments. It's excellent. Okay, the mass. We have masses of protons equal to 1 AMU. That stands for atomic mass unit. Atomic mass unit. Neutrons are also 1 AMU, 1 atomic mass unit. Electrons are approximately 1 over 2,000 AMUs. So for all intensive purposes, we say that the electron weighs about 0 AMUs. When we're figuring out the mass on the periodic table, it's pretty much negligible. Yeah.
What is an AMU?
It translates over to approximately the masses that we get on there. So the carbon atom there has 6 protons and 6 neutrons pretty much, which is why it has a mass of 12. Good question. Thank you, Elliot. Yeah, Duncan.
If atoms are
Yeah.
elements and stuff, what exists between the electrons?
So if I have a whole bunch of atoms of the same type of atom that make
overlap?
they sometimes do. If we're going to talk a lot about the bonding later. When we talk about bonding and metallic bonds versus ionic and covalent bonds, we're going to get into all of that, what's actually going on in the molecular level. At this point, I don't want to talk about that too much. Good question. What I would like to have you notice is that the majority of the mass is in the nucleus. Almost all of the mass is in the nucleus. And if we're looking for relative things again to put this onto a scale that we might understand, we can think about the nucleus. If I had a 1 centimeter diameter sphere and I was able to fit 133,000 tons into that 1 centimeter sphere, that's about how dense the atom's nucleus is compared to the rest of the atom. Which would be like saying I'm going to take about 1,500 aircraft and shove them into a space of a 1 centimeter diameter. So we've got something really dense here compared to the atom overall. Dense nucleus. Dense nucleus compared to the atom overall. What other questions do you have so far? You've had some good ones that I'm not willing to answer yet. Some good ones that I have answered. Okay, let's move on then. So, the nuclear symbol. You are going to be asked quite a bit to write the nuclear symbol for different elements. And what a nuclear symbol incorporates is an atomic number, the Z, which is the number of protons. Which, if we have an atom, which atoms must be neutral, we must also have the atomic number equal to the number of electrons. This again is only if we have an atom. Only if we have an atom.
In what situation wouldn't we have an atom?
When we have ions. We're going to talk about that very soon. Thank goodness for ions, otherwise we wouldn't have table salt. Okay. We also write our nuclear symbols with the mass number A, which would be the number of protons plus the number of neutrons. Now on the periodic table, you can see, let's look at helium. 4.00260 is my mass. Does that mean I have, if protons are 1, neutrons are 1, and electrons are basically 0, does that mean I have 0.0026 of either a proton or a neutron? No. We're going to talk very soon about what an isotope is. We get that number based off of the ratios and the relative abundance of the different types of isotopes that we have. That helium atom, in general, most of the time has 2 protons and 2 neutrons. Sometimes it has 2 protons and just 1 neutron. And that's what gives it that odd number. So, when we write mass number for our nuclear symbol and it's just number of protons and just number of the neutrons, this is always a whole number. Never a decimal. You might see something like this. If I have Cl35, you might ask me to write the nuclear symbol for Cl35. It's a little hard to read, sorry. Cl35. So, if it says, write this, oh, I want the size. There we go. Nuclear symbol for it. I start out by writing the symbol for chlorine. And I'm going to write the mass number on top, so my A number on top, my Z number on the bottom, and my symbol. I'll do S for symbol. That's my general format. What was that? No, this is my general format where that's the symbol. This one is my actual example where chlorine is my symbol. So I need to look at the periodic table. What is the atomic number for chlorine? Shout it out. 17, yeah. 17 is my atomic number, which means 17 goes on the bottom here. And this number here, 35, this is telling me which isotope of chlorine I have. So that means that I have a mass of 35. So if I have a mass of 35 and I have 17 as my atomic number, how many neutrons do I have? Yeah, 35 minus 17. 18. Because the mass number is the protons plus the neutrons, so that means my number of neutrons would be equal to my mass minus my protons. Duncan.
Why don't we account for electrons?
Because they're almost zero.
But when you get to numbers that have like over 100, an over 100 atomic number, wouldn't the number of electrons start to slightly affect the atomic weight?
Not enough. 1 over 2,000 isn't enough to make a noticeable difference. Good question. Elliot.
What do you do if you're not given the isotope?
Then you can't answer the question. You'd have to be given number of neutrons, perhaps, or you wouldn't be able to answer it. Yep. And since this is an atom, it's not telling us that it's an ion. How many electrons would this chlorine have?
35.
Would it?
Oh, wait, you said it's not an ion?
Yep, it's not an ion, it's just an atom. So how many electrons does this chlorine have? 17, yes. 17. Protons equal to electrons, so 17. Good. What questions do you have so far? Yeah, Jamal. We are going to do a different way of looking at an example, yes. Okay. So you have another chart. And what we are going to do is fill out this chart. Erin, can you put the book away, please? Thank you. So, first one we're going to look at, AS. Who remembers what AS stands for? Arsenic. Good. So, you need to find arsenic on the periodic table. How many protons does it have? 33. Yeah, it's the atomic number. I'll write that up here just in case we're forgetting. The number of neutrons I'm going to figure out by doing 75 minus 33. What do we get?
42.
Yeah, 42, the answer to life, the universe, and everything. Now, this isn't saying anything about a charge. We haven't dealt with ions yet, so we're going to assume it's not an ion. So, how many electrons do we have? 33. Yep, again, protons and electrons are going to be equal so that it can be neutral if we have an atom. Good. So if I wanted to write out my nuclear symbol for this, what number would go on top? 75, yep. It's always going to be the bigger number on top, because the mass is always going to be bigger than the atomic number. So 75, and then what's on the bottom? 33, lovely. Okay, this next one just tells me the mass number and the number of protons. How can I figure out what element it is? Do I look at the mass or the number of protons? Number of protons. Some of the masses are pretty similar, so we look at the number of protons, which is the same as what? Potassium. Yes, for this one it is potassium. Potassium, and we can fill in the rest of our nuclear symbol because we already know that the mass is 39 and the atomic number is 19. So how many neutrons do I have? 20. And how many electrons? 19. Excellent. Okay, the last one, I just have the number of neutrons and the number of electrons. Well, we're assuming that it's an atom, so electrons are the same as protons, which is the same as the atomic number. So what element am I dealing with? Iodine, yeah. Iodine. Iodine has an atomic number of 53. So I can write 53 for my number of protons or atomic number, and I can put 53 on the bottom here. What two numbers do I add together to get the mass? Protons and neutrons. So 53 plus 78 gives me what for my mass?
131.
131. Thank you. On what? Ah, excellent. So we have a different isotope. And we're going to see those different isotopes very soon. Yep.
How do they get decimals for the masses of the atoms that you just calculated as that?
Yep, from the different isotopes that are there, which is what we're going to talk about very, very soon. Okay. What other questions before we move on to ions? Yeah. Yes, but you're going to be given more information with the next slide. Good question. Okay, so let's take a look at ions now. Ions are atoms with a charge because we have an unequal number of protons and electrons. Okay, we have cations and anions. Cations are the reason that I have Hello Kitty everywhere and why I wore Hello Kitty for Little Kid Day. So a cation is a positively charged ion.
So that happens when it has more protons than
Yeah.
electrons.
Yep, exactly. So more protons than electrons, which means it has lost electrons. It doesn't mean that it's gaining protons. We're not doing nuclear chemistry here. We're doing regular chemistry. So the only thing that we can gain or lose are electrons. Oops. So in regular chemistry, all we're doing is gaining or losing electrons. We're not changing the number of protons, because what would be changing if we change the number of protons? The element. Yeah, if we change protons, we change the element. Sorry, delta is a change. We change the element. Little shortcut for your notes. Delta means a change. So if we change the protons, we change the element. So the only thing that we're either gaining or losing are the electrons. The things that lose electrons on the periodic table are metals. They are prone to losing electrons. And we're going to talk about why that is. Yep, it's only going to be the metals. And we know the metals are the majority of the periodic table. They're anything to the left of the staircase, which on that big periodic table there is the drawn in yellow and blue line. So everything to the left of the blue are metals. The majority of the periodic table are metals. Yeah.
And then, sorry, you said the metals were the ones that lost the electrons?
Yep. Yep. To form cations. Yeah, Elliot. Hydrogen is an interesting case. They didn't quite know where to put it. And we'll talk about that more when we're talking about some of the properties of the elements. That's why it's just an oddball. It can gain electrons, it can lose electrons depending on what it's around. It's just odd.
Why is mercury blue and all the other ones are blue?
Excellent question. So the question is, why is mercury blue? It is because it is a... Oh, go ahead.
It's because it's a liquid.
Yeah, it's a liquid at room temperature. So the red ones up there are all gases at room temperature. The blue ones are liquid at room temperature. And you can see most of them are solids at room temperature. If they are white, those are our ones that don't really form easily. They have to be made. They're very, very rare. What, Katie? Most of them are.
And
Yeah.
don't some of them like
Yeah.
not even really exist?
Yeah, yeah. Once you get to those new ones that are up there, the DS, RG, CN, FL, and LV, those have just recently been named because they haven't really. They exist for milliseconds most of
They
the
got
time.
those W names.
Well, because
What was that?
they found one with the
The names, you know, you tape those over, kind of like you, one of those, yeah, how do they get those?
The UU. Oh. The UU names that they have, like 118, that is the Latin name something. It's the Latin name for 118. I don't speak Latin, sorry. So until somebody decides to name 118, which it goes through a huge process, there are hundreds of scientists on the IUPAC board that decide what these things get named. And 2 of them were just recently named over the summer. 2 more of them were named over the last school year.
This one's called, I remember down here, this one's called Californium.
Yep.
And this one's called Einsteinium.
Yep, yep. And
Yeah,
berkelium is right
Yeah,
next to
Americium.
California.
Nobelium.
Yep, yep.
Who's met-
Lots of fun ones.
Design
The periodic table. Yep. Okay, let's move on to anions. Those, oops.
Like Einsteinium.
That is a fun one. Anions have a negative charge. So it is a negatively charged ion, which means it has more electrons, oops, than protons. Which means it has gained electrons. And these are my nonmetals. So the little part of the periodic table to the right of the staircase until you get to the noble gases, which are really stable and don't want to accept or lose electrons. Until you get really, really big, like radon, we can form some compounds with. Xenon tetrafluoride, actually, we can form some with. What was that, David?
Why is radon's mass intensities?
Because it's not quite determinable by the methods that we have. Elliot?
Does that mean like the 118 is stable?
No. No, that one is very, very unstable. And 118 has been up for debate as to whether it had actually been found or not for a long time. Somebody thinks that they just verified that you could form it with, I can't remember what they used, maybe tin atoms, something like that. That's been recent in the news too. Yeah, exactly. For a millisecond, I've got proof. Okay, so let's look at some ion things. So this is just slightly different from what we saw before, but it had to give us more information. So, nickel, looking at the periodic table, has how many protons? 28, yeah, I heard it, thank you. 28 protons. So I can put my bottom number here as 28. My mass number, it says here, is 58, so my neutrons is 58 minus 28, which is what? 30, yeah. Now, my electrons, if I have a positive 2 charge, it means that I have lost 2 electrons. Oops. Yeah, so it's 26. So I take 28 minus 2, and I get 26 electrons. Okay. My next one, I have phosphorus. What's the atomic number of phosphorus? 15. So I have 15 protons. I have 31 minus 15 neutrons. How many is that? Excellent. 16. And my electrons are not the same because we have an ion now. Have we lost or gained? Gained. Yeah, we gained 3. So I take 15 plus 3. What do I get? 18. Excellent. What number do I put on the bottom here? 15.
Why aren't those included in these kind of diagrams?
You know, I don't know why they weren't. That's a good question.
Is it just like a thing on this worksheet?
On this worksheet, yeah.
You're supposed to?
Yeah.
No.
Yep. We would normally have them in, but this was just to get ready for stuff. So we're filling it in as we go. Okay, which element has 11 protons? Sodium, yeah, Na. Is sodium a metal or a non-metal? It is a metal. So are we going to be gaining or losing electrons? Losing. So is our charge going to be positive or negative?
Positive.
Positive, yes. And if we look here, I'm going from 11 protons to 10 electrons. So yeah, my charge is a 1 plus. I have lost 1 electron from the atom that it was before. Na 1 plus.
So it's 1 plus, not plus 1.
Excellent. I was hoping someone would ask that. Thank you, Ben. Yes, we always do the number first because otherwise it looks like we're trying to add 1 to our element rather than saying that we have a charge of 1 plus. That's just the standard form for it so we don't get confused about things. Thank you for checking that. I was waiting for someone. Yes, Nikki. What Ben was just asking? He was asking why... No?
I didn't say that.
Okay. No worries. But it is a metal, so it lost electrons. That's good. Yeah. We'll see when we get to the 2, 3 notes. For right now, I'm just going to tell you that metals lose. Yep. Okay, we need to finish out my diagram here. So what number goes on top? 23, yeah. How did we get that? Added protons and neutrons. Good, and what goes on the bottom? 11, yeah, the atomic number of protons. Excellent. Okay, my next one has 17 protons. What element is that? Chlorine, yeah, Cl. And it's a non-metal, so it's going to gain electrons. And we have a 1 negative charge. So, what is the number of electrons I have? 18, good. What number goes on top? 37. And what goes on the bottom? 17. Awesome. What other questions do you have about that before we move on to isotopes? Like the Springfield isotopes. Did you guys realize that you have never been on this earth since there's been no Simpsons? I can remember a time when there were no Simpsons. You have always been around with the Simpsons. Katie. Is it? We are. Yep. At least we better.
My dad's even only been around for 2 years longer than there was Doctor Who, which is crazy.
That is crazy because that's been around for quite a while. Cool. Okay. Oops. What just happened? Go back. Okay. Isotopes. We know that protons have to remain the same. We talked about this with ions as well because we're talking about the same element. But we can vary the amount of neutrons that we have. So it's going to have the same chemical properties because it has the same number of electrons. And it's going to have slightly different physical properties, like its density. Wow, that was a very weird Y. It was squiggly. Most of the pens. So, We have the same number of protons, different number of neutrons, and that is what gives us the average atomic mass, which is the decimal on the periodic table. So average atomic mass are due to the isotopes. And we can calculate the number that we would find on the periodic table, bless you, based on relative abundances. So the average atomic mass is why we have decimals, not whole numbers. So when we calculate it, we need to convert the percentages to decimal form, which just means we're going to move the decimal place over 2 and multiply it by, the mass that we have. And then add it to whatever our other ones are, and its mass. Yep, we're going to go through it here. So I'm going to convert this percentage to a decimal, which is 0.25. And that's going to be multiplied by the number that I have for the mass, which is 37 here. So 25% of this isotope is 37. And it's chlorine, so that means I have 17 protons and 20 neutrons in this one. And then I add that to my other one. So 75%, or 0.75, of a sampling of chlorine, if I had a sampling of chlorine in my hand, 75% of it would have a mass multiplied by 35. So 17 protons still, because it's still chlorine, but now I only have 18 neutrons. So I calculated out, I get 9.25 for my first bracket there, and I add it to 26.25, and I get 35.50, which is relatively close to what I have on that periodic table. A lot of the time we have many more isotopes than these. Sometimes we only have 2. I'm not going to go through the example of iron. Do you have the example of iron on there? You can try that one at home, and I will podcast it and put it up, like I will put this up. Remember, to see my videos, go to YouTube, search for Jen the Chem Lady. All of the demos that we do and all of our notes are up there. Jen the Chem Lady, which is also my Twitter handle if you want to follow Saturday study tips and Wacky Science Wednesday and other things that I end up posting that can be helpful.
If I follow you, will you follow me back? I got to keep my ratio up.
I will think about it.
It's like a book.
Oh no. Oh, funny. Okay, so we're skipping that one for right now. What I do need to tell you before we get going today is about radioisotopes, because every IB test that I have seen since they changed this syllabus around has had a question based on radioisotopes. They always do. It's either a very short answer question or it's a multiple choice question, but I have seen it on every test since this syllabus was made in 2005. So I want to make sure we get to it today. So radioisotopes are radioactive, which means that the nucleus is spontaneously going to start breaking down. They occur naturally and are produced from stable elements by exposing them to a stream of slow-moving neutrons in a reactor to gain more neutrons. Some of them occur naturally, some don't. And we use them for carbon dating. We use carbon-14. So if we have a really old relic that we're trying to decide, well, is this really dead body? Like, is this really King Tutankhamun, or is this somebody trying to make King Tutankhamun by mummifying someone nowadays. We can look at the bones and the amount of carbon-14 isotope that's left in there to determine whether or not it's of the age that it's supposed to be. We use them as tracers, which used in medical things. So iodine 125 and iodine 131, bless you, can be used to determine the activity of your thyroid. So if you think you might have a thyroid problem, sometimes they'll test to see if you have a thyroid problem with this radioactive isotope. And radiation is used to treat cancer, commonly with cobalt-60. So those are some of the uses. Those will come in handy for you. You have a homework worksheet that is due tomorrow. What else is coming up tomorrow? A mini quiz. And what else? We're going to be in the lab. Yay! Another lab day. It's not computer lab. It's just a regular in the lab wearing goggles lab. Not a formal